I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life,
the universe.
Hello, this week we're celebrating 150 years of the periodic table. We'll find out how scientists uncovered the elements in the first place and what other mysterious materials are just waiting to be discovered.
Plus, a way to power up the body's own morphine-like chemicals, how microbes are gluing microplastics back together in the ocean, and post-Valentine's Day, some dating do's and don'ts to bear in mind for next year. I'm Katie Haylor.
I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, millions of people are affected by chronic pain, and despite this, we're not very good at treating it. But a discovery by scientists in France that's enabled them to power up the pain-killing effect of the body's natural morphine-like chemicals and target the effect to where in the body it's needed means we might be about to become much better, as the old saying goes, at hitting pain where it hurts.
Peter McNaughton is a pain specialist at King's College London. He wasn't involved in the new study, but he agreed to take a look at the paper and he told Chris all about it.
What this group have set out to do is to find out an alternative to the opiate class of drugs, morphine, heroin, etc. Now, these drugs are fantastic painkillers. They work really well, but they have a number of huge downsides. They cause addiction, they cause respiratory depression, which can cause people to die in their sleep. And these adverse side effects are all caused by penetration of morphine, etc., into the central nervous system.
And what you're saying, it's because they get into the brain and spinal cord, the central nervous system, that we get that downside. If we could stop that, that wouldn't happen.
Exactly, and that's what they've tried to do. They've invented it's not really a new drug, it's a new twist on an old theme. What they've invented is a drug which doesn't enter the central nervous system and therefore shouldn't have all these nasty effects that we talked about a moment ago.
How does it actually do that?
Well, they've done it by using what's really an old idea, which came from Hans Kosterlitz, who was working up in Aberdeen. Kosterlitz found that there is an endogenous opiate produced within the body, and he really discovered this just with a very simple piece of reasoning, which is that drugs of the opiate class, heroin, morphine, etc., are so potent that they must be latching on a system which exists within the body already, and isolated some peptides which are called the enkephalins.
So these are compounds which are naturally present in the body, and they activate the nerve pathways that morphine, when we inject that, does, and that's how they achieve their pain-killing effect, the difference being that you can make those compounds yourself.
Exactly. These are the endogenous opiates, as they're called. They have a powerful analgesic effect. You can see why this is important from an evolutionary point of view. If you're in a highly stressful situation, you're being chased by a bear or something like that, there's no point in saying, oh, ow, stop, the bear's biting my ankle. You've got to get away, otherwise you're going to die. And therefore, in stressful situations, the release of these endogenous opiates give a tremendous analgesic effect, which means effectively that you can escape a life-threatening situation.
And the group are exploiting those compounds and the way in which they work in order to produce this new way of doing pain relief.
Exactly. The enkephalins are peptides, and these are compounds that are metabolized very rapidly in the body. So they produce an analgesia which is very short-lasting. So from that point of view, there's not much point in injecting enkephalins into people's bloodstream. The analgesic effect will be gone in a couple of minutes. What this group have done is they've linked up enkephalin with a lipid, a natural body lipid called squalene. They found that makes the lifetime of the enkephalin very much longer. And the other advantage of squalene is many squalene groups sort of make a lipid droplet, which is sort of like a hedgehog, got the enkephalin sticking out. And this produces a very long-lived form of enkephalin, even longer-lived than morphine.
So if you inject it, it will circulate for a long time. It can bind onto all the right nerve endings and block the transmission of pain, but it doesn't seem to get into the brain and spinal cord and cause the adverse effects of morphine.
Exactly. And in fact, one of the things they've shown, which is even more interesting, is this circulating lipid droplet with the enkephalin peptides attached seems to be targeted specifically to areas of pain. Now, it's been known that when you have local inflammation that causes pain, that makes the blood vessels more leaky. And it's at those specific spots where the blood vessels are leaky that the compound is able to leak out and have its analgesic effect.
How have they tested it to prove that it is actually as good as that?
They've attached a fluorescent compound to their enkephalin squalene drug, and they've done whole body imaging of animals, and the drug accumulates in areas where there's a localized inflammation that's causing pain, and it doesn't accumulate in other places.
And can they also prove, though, that in those animals they're not feeling pain because they've injected this?
Well, and not in exactly the same animals, because the animals that are being imaged are unconscious. But parallel groups of animals, they've been able to find that pain is very, very much reduced by the injection of this enkephalin squalene complex.
Will it work in a human?
Well, it should do. Of course, we don't know that. These are animal experiments, but I can't see any reason why it wouldn't work in a human. I just have to point out a downside of this method of getting the drug on board to the patient, that it has to be injected intravenously. And if you're treating a soldier in a battlefield situation, that's something that's going to be rather difficult to do.
Notwithstanding that, though, still sounds like it could be extremely useful, doesn't it? Thank you very much to Peter McNaughton. And the paper that Peter was commenting on was published in Science Translational Medicine. It was by Patrick Couvreur and his colleagues at the Paris-Sud University.
Now, human papillomavirus, or HPV, is the name for a group of viruses that commonly cause verrucas, warts, genital warts and cervical cancer, and they are very common. The infection usually resolves itself, but in some cases it leads to damage to the DNA in the infected cells, which can result in cancer. This is why we have a screening programme to look for these changes and to try to pick up the disease early before it can spread.
Now, just over 10 years ago, a vaccine against the highest risk forms of the virus was introduced. In Australia, boys and girls received it, but in other places, the UK is one of them, it was given just to the girls. But 2019 is going to see it being offered now also to boys in many places, as well as changes to the way that we screen for the infection. Margaret Stanley helped to develop the vaccine. She's an HPV expert based at the University of Cambridge, and she's with us now. So, Margaret, what do the data show in terms of the 10 years since this vaccine's been introduced? Does it work?
Well, I can give you the information from the UK, and the UK has had a spectacularly successful vaccination programme, and we're seeing the results of that now. And I can quote what's happened in Scotland. The girls who were vaccinated in 2008 in Scotland, aged 13, 14, by the time they were 20 in 2015-16, came up for their first cervical cancer smear, because in Scotland at that time you were getting smears at 20. So we know what proportion of those girls we expected to have the pre-cancer, that's what the screening programme is about, and what proportion did. In fact, there was a reduction of 86% in the pre-cancers in that group of vaccinated girls. That's spectacular. Part of the reason why is in that young group of girls, those two very high-risk viruses that the vaccine targets are the ones that cause most of the precancers and the cancers. So the vaccine is stunningly successful. The same data from Australia, same data from Denmark. Wherever you've got a high vaccine coverage, and I want to emphasise that, we've been really successful in the UK because almost 90% of our 13-year-olds are vaccinated. Whereas in other countries where it's much lower, you're not getting the result.
Yes, so the data you've quoted is for people who have been vaccinated against people who would have been otherwise identical to that group and haven't.
That's
so
correct.
If we look at those people who haven't, roughly what number of cervical cancers are we seeing, or pre-cancers are we seeing in those people normally?
The pre-cancers sort of peak in the 20s. You expect to see about 2 per 100 individuals for the precancers. Now, not all those precancers go on to cancer, but those 2 individuals will have to be treated. So what we're doing is taking out almost all of those precancers losing that treatment. If you haven't been vaccinated, however, you've got to be screened. And you still ought to be screened even though you're vaccinated, because not all of the HPVs that cause cancer are targeted by the vaccines. But your risk is massively reduced.
What was the rationale? Was it just cost for only going for the girls and not vaccinating the boys in countries like the UK?
Well, it's because genital HPV is a sexually transmitted infection. And if you immunise one gender, then you protect the other gender. And so decisions about who to vaccinate when and how many is based on modelling and on health economic policy. So if the models said, well, if you can get up to 85-90% of girls vaccinated, we won't need to vaccinate the boys. But it turns out that men get cancer of the throat, which is caused by HPV, and they're 4 times more likely to get it than girls.
And the vaccine will stop that?
Well, I have to be very careful. I have no data from trials that says that the vaccine will stop the cancer. I can tell you that the vaccinated people lose their infection in the mouth. So it prevents the infection in the mouth. And, I'm a simple soul. If you don't have the infection, you won't get the cancer.
Now, you mentioned that the vaccine represents some of the highest risk forms of the virus.
Yes.
But it doesn't cover all of them.
No.
So we're still having to do cervical screening. Why can't we add the missing viruses into the vaccine if it's so successful?
Well, there's a second-generation vaccine which is commercially available, and that's the one actually which is now being delivered in Australia and the USA. But the decision hasn't been made yet in the UK as to whether to put that into our programme.
And that does represent these other forms that are missing at the moment.
Well, it represents the sort of global take on this is the vaccine that targets the 2 high-risk viruses, which is what we currently use, will get rid of 70% of cervix cancers worldwide. You put this other one in, which has another 4 high-risk HPVs, you'll get rid of up to 90% of cervix cancers worldwide, but you'll still have a little rump of cancers which are not covered by the vaccine.
So we still need to screen. And that brings me on to my other point, which is, can we use the learning that's gone with the study of human papillomaviruses together with much better diagnostic techniques that we now have? We can screen for DNA and things like that now, rather than just having to look at cells under microscopes. Can we use this knowledge to do a better screening job now?
Yes. The screening programme in England and the rest of the UK is going to change in 2019 from the first analysis being looking down the microscope at cells to, in fact, detecting DNAs of these high-risk viruses. You'll still come for your smear at 25, but instead of that smear being looked at by down the microscope first, it will be tested for DNA. If it's DNA positive
for the virus,
then the screener will have a look at those cells. And if the cells are normal, then you'll go back into the program and be asked to come back and have another screen in about a year's time to make sure you've got rid of the virus.
If it's negative, you need go no further at that time.
Absolutely.
So it's going to save loads of money and time.
It's not only that, it's going to save all the hassle of getting for a smear. And it's a much easier and much more convenient. More importantly, it's more sensitive. The trouble with cervical screening is it's a wonderful public health intervention, but although it's very specific, it's not very sensitive.
Margaret, we must leave it there. But you told me when you came on this programme 14 years ago and talked about this vaccine that was going to happen, it was going to be a game changer. It looks like you were right.
I think so.
Margaret Stanley from the University of Cambridge, thank you very much.
So what we were trying to do with this paper is to demonstrate the ability to type using brain signals, anywhere between approximately 4 and approximately 8 words per minute, a factor of between 2 and 4 faster than what's been demonstrated before.
Each month, the eLife podcast talks to some of the world's best scientists. Join me, Chris Smith, as I hear about breathtaking discoveries hot off the press. Find the eLife podcast on iTunes or listen and download for free from nakedscientist.com/elife. Still to come, a new twist on microplastics in the ocean, and how do chemists tell one element from another? We'll be finding out.
Into space now, though, and the magnetosphere is a protective layer that surrounds the planet. It's formed by charged particles rushing in from the sun and interacting with our magnetic field. 45 years ago, a theory was set out suggesting that when it's hit by a surge of radiation from the sun, the whole magnetosphere shakes like the surface of a drum. This, the theory says, produces electromagnetic radiation that can have consequences for systems here on Earth, including our technology. And this week, scientists have proved this really does happen. Adam Murphy has the story.
The sound you just heard is streams of charged particles travelling at 400 kilometres per second from the sun, hitting our magnetosphere. The magnetosphere is a layer around the planet formed when particles from the sun meet our magnetic field. It helps to protect our planet and our technology from the harshest effects of these solar streams. And just like striking a drum, when streams from the sun hit this magnetosphere, they make ripples in it. Martin Archer is a planetary physicist from Queen Mary University, London, who's been looking into a 45-year-old theory about the Earth's largest drum.
What we found is some of those ripples which will head towards the northern and southern poles will get reflected back, and you'll end up getting a pattern called a standing wave that's very much like how you get patterns on the surface of a drum and what gives them their notes. So that's what we found about the magnetosphere in this particular study.
A standing wave is a wave that looks like it's standing still, like a guitar string, or in this case, a drum.
The way that we drew this picture together was by using 5 different satellites from NASA's Themis mission that happened to be in the right place at the right time and essentially allowed us to see the thing hit the Earth's magnetosphere, see the boundary move in response, and hear the sounds within our magnetic environment that were caused by it. So it was piecing together those observations that allowed us to finally make this discovery.
But since particles from the sun are always hitting the Earth, how do you isolate one single solar slam?
It's a complicated problem being able to show direct causality from one thing to another, often because you've got lots of things happening at the same time all at once, lots of different processes that can lead to something quite complicated. So that's why we picked a very specific sort of impulse. It was a very strong jet of plasma hitting into our magnetosphere with nothing really very much either side of it happening. So that means we could be very clear about that it was definitely this and not something else going on that was causing the effects that we saw.
And understanding this, it isn't just pie in the sky stuff.
So the consequences of this are things that we still need to do a bit more work into, but we certainly know that these standing waves do penetrate into our magnetosphere quite deeply, and they're a source of ultra-low frequency waves.
So when these streams from the sun hit the magnetosphere, they cause all the charged particles there to wiggle, which creates these waves in the magnetosphere itself. And these help create ultra-low frequency waves, which may have profound effects on our technology.
They can accelerate electrons in the radiation belts up to energies that can damage satellites, for instance. And there are ideas as well that these waves might affect the aurora and they can actually heat the top of the atmosphere. So there's lots of different ways in which it could have consequences, mainly on our technology. But as I say, because we've only just discovered these in the observations now, we've got a long road ahead of us to do further research into really understanding the actual implications.
So watch this space. That was Martin Archer, and the work has just been published in Nature Communications.
Now, back down here on Earth and into the ocean, in fact. Small particles of plastic called microplastics and nanoplastics are being formed when larger bits of plastic rubbish are breaking apart. At the moment, we don't know what the consequences of this are going to be.
But one outcome that scientists have now documented is that sticky polymers produced by microorganisms can glue these smaller plastic particles back together, so they form bigger agglomerations that other species mistake for food. Mariana Campos spoke to Tony Gutierrez, who's been studying the effect at Heriot-Watt University in Edinburgh.
We were interested to understand what happens to nanoplastics in the marine environment. And we observed that, like with microplastics, they form into agglomerations. With biopolymers, these are gluey, sticky substances that are produced and released by bacteria and microscopic algae or phytoplankton in the ocean.
How did you get to the results that you got?
What we did was we incubated natural seawater with some nanoplastic particles. Within hours, we observed the formation of particles. And these particles grew in size. And we could see these nanoplastic particles embedded within a web of polymers. And what we wanted to find out after this was what type of polymers could be enveloping these plastics. So we extracted polymers from a particular species of marine bacteria that produces a lot of these polymers, and we incubated them with the plastic particles, and indeed we observed the very quick formation of plastics embedded within this web of polymer.
Are the agglomerates dangerous?
We don't know what their impacts could be. One thing we know is that what were invisible nanoplastics have become visible by the formation of these agglomerations. So what this could lead to is these particles, which are now visible, could be mistaken or seen as a food source and ingesting the plastics that are within them. We don't know what the impacts could be. We do have some data that suggests that there are no toxicological effects, but we still need to do more experimentation to understand that.
Have you got other experiments planned for the future?
Yeah, so one thing we want to look into that I'm very interested in is in the formation of these plastic agglomerations, does it have an effect in terms of the degradability of the plastic particles? So could these agglomerations be a hot zone in the marine environment where the plastics could be broken down or degraded faster by the microorganisms that are associated with these agglomerations? So that's certainly something I'm very interested in doing. What I'm explaining is something that's occurring naturally in the environment. How to enhance that to get rid of plastics, that's something that really deserves a lot of thinking. I think we still need a lot more information. But one thing at the end of the day really is in order to reduce the concentrations of nanoplastics and microplastics in the environment, we just simply need to reduce the entry of plastics into the oceans. So implementation of policies and so forth that really reduce the amount of plastics that go into the environment.
Tony Gutierrez, and that paper was published in Marine Pollution Bulletin.
We've just kissed goodbye to Valentine's Day for another year, and if it didn't quite work out the way that you planned this time around, then perhaps you need to alter your approach. And to set you on the right track, we sent Katie to see social psychologist and dating expert Viren Swamy at Anglia Ruskin University to hear his top tips for dating do's and dating don'ts, starting with that old chestnut, playing hard to get.
In general, playing hard to get doesn't work because it contravenes what's called theory of reciprocity, that we like people who like us and we dislike people who dislike us. So if you show any form of dislike for someone, like playing hard to get, the theory is they will dislike you in return. Now, it's slightly more complex than that. They may want you a bit more, but they may not like you very much when they get you. You want to give the impression that you like that person because liking sparks liking in return. The best suggestion is to play selectively hard to get, to show the other person that you like them as an individual, but that it's actually very difficult for other people to get you.
Another piece of advice is to date someone who is very different from you. This idea of opposites attracting, can we bring out qualities in each other? What do you make of this?
There is zero psychological evidence to suggest that opposites ever attract. It's a very, very old idea. In fact, about 60% of general public believe that your ideal partner is someone who has the opposite qualities to yourself. All the studies from psychology suggest that the more alike two people are in terms of their demographics, in terms of their values, in terms of their maturity, in terms of their life goals, the more likely they are to get along.
But that doesn't necessarily mean you have to be very, very similar, does it?
In the short term, no. So on a first date, you want to be with someone who is relatively similar to you, and perceived similarity is probably more important. So you both think that you're relatively similar. If you end up having a relationship, most couples tend to engage in something called attitude alignment if they're invested in the relationship. If, for example, you and I disagree on Brexit and we're in a relationship, we'll find some common ground or minimise the things we disagree on.
That's some do's. Don'ts, a big one I've come across looking online is talking about your exes. This has got to be a no-no, right?
Absolutely. On a first date, you don't want to put all your stuff out there. It shows that you're still stuck in the past. It shows that you're not really ready to move on and have a positive relationship with someone else. You might also want to think about why it is you're talking about your ex on a first date. Are you just looking for someone to listen? In which case you might want to talk to your friends rather than a potential partner.
Another don't. Spaghetti bolognese, pizza. Are there really any hard and fast rules about food that you should eat when you're on a date?
The thing with rules is I hate rules. Human beings are so complex and we're just so complicated that you never know how someone's going to react. Someone else might find your sloppiness, your messiness with spaghetti bolognese really cute. Another person might find it really disgusting. So it's really difficult to know. The important thing is, if you're planning a first date, to both decide together where you'd like to go. And if that's a messy food place, then hopefully you'll both enjoy it.
Obviously, this is quite light-hearted, but there is a bit more of a sinister side to dating advice. I've come across a concept called negging.
So negging is an idea that comes from pickup artistry. Pickup artistry more generally is this idea that's typically sold to men that they can program women to behave in particular ways as a result of particular use of language or particular behaviours that they do. Scientifically, there's no evidence to support it. It's considered pseudoscience. One version of that is negging. Pay a woman a backhanded compliment, and that will make that woman want to come to you even more.
So is this something like, wow, you're a bit cleverer than I thought you'd be by looking at your picture?
It's more along the lines of, you look really horrible, but at least you're a nice person. From a scientific point of view, it contravenes the theory of reciprocity. If you're horrible to someone, they're not going to like you in return. You want to show you like that person. I think a lot of the kind of pickup artistry is based on misogyny. It's this idea that you can program women to listen to men's use of language and respond in return. It's all nonsense.
Is there one piece of advice you'd give people to have a nice date?
Just be a nice human being, be a decent person, and treat other people with respect. There is a good reason why this is important, and it's based on the halo effect, this idea that we transfer perceptions of a person's characteristics onto some other characteristics. So if, for example, you're perceived as being a nice human being, sometimes that also transfers into perceptions of your physical attractiveness. In very simple terms, if you're a nice person, in the long term, you also get perceived as being more physically attractive than you actually are. Second reason why it's really good to be nice is it just makes everything better. Particularly if you're going on a first date, it can be really stressful. Just being nice makes everyone feel better about themselves. There is another thing you can do, which is to get your partner to hold a warm cup of tea or coffee, because the idea is that they will transfer the warmth that they're feeling into your personality. Essentially, they will come to think of you as being warmer than you actually are.
That's genius.
But don't make the tea too hot, though. It's not a dose-dependent relationship. Thank you very much to Viren Swamy. He was giving his dating do's and dating don'ts to Katie.
And if you'd like to find out more, all the transcripts and papers can be found on our website, nakedscientist.com.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
In the next half an hour, we're saying happy 150th birthday to chemistry's best friend, the periodic table of elements. But what actually is an element? With the quickfire science on the subject, here's Jenny Gracie and Adam Murphy.
Do you remember that giant wall chart that stared at you during science class at school? Like a game of Tetris, the lines of different colour blocks slotted into a grid, with a few more lines of blocks below. This chart actually shows all the building blocks or elements that make up everything on Earth, from the microphone I'm speaking into to the ears that you're listening with. This special table tells scientists how these elemental building blocks behave.
But what actually is an element? Each element is made up of one type of atom, and each is given a letter, like H for hydrogen or O for oxygen. Atoms have three basic building blocks themselves: protons, neutrons, and electrons. In the centre, the nucleus, you'll find the positively charged protons and neutral neutrons. So to balance the charge, whizzing around the nucleus are layers of negatively charged electrons. What defines one element from another is how many protons it's got, called its atomic number. Hydrogen has 1, oxygen has 8, and you'll see this number next to each symbol on the periodic table.
Now, the vertical columns in the table are called groups, and these can be thought of as element families. Each group has the same number of electrons in its outer layer, which tells us how it might react with other elements. The first group all have one outer electron, and these often react violently with water. Group 2 have 2 outer electrons, and the pattern pretty much continues across the table. It is these outer electrons that form bonds with other elements, and also what determines the shared properties of a group.
Some elements, like iron, copper and gold, have been used by ancient civilizations for thousands of years. To date, there have been 118 elements discovered. To mark its 150th birthday, we're taking a tour of the periodic table, asking how we tell one element from another, are we using elements sustainably, and what might the future hold for life's essential building blocks.
Thanks, Adam and Jenny. So, in a nutshell, the periodic table is essential for all chemists, and it's an important tool for predicting how the elements we have around us are going to react. But how were the elements that we know and love actually discovered in the first place, and who put that table together? Peter Wuthers is a chemist at the University of Cambridge and is with us to explain. Where did it come from?
Well, actually, it took quite a while to develop. I mean, it didn't just appear in one go, and actually a number of people independently discovered this, all around the same time, actually, in the 1860s. But there was a long time leading up to that different forms began to emerge, in a sense.
How did people realise that there was this relationship between the elements that we see around us and that we could arrange them into a table like that?
Well, people were beginning to look for some sort of structure in the elements and the similarities that they had way before the periodic table itself came about. So, for instance, there's certain elements that were recognised as having very similar properties. Some of these, for instance, were the so-called alkaline earths. And actually, even before they were identified as elements in our modern sense, their compounds were recognised as having very similar properties. And eventually, when the metals were discovered, they were called the alkaline earth metals because, again, they all shared similar chemical properties. Similarly, the alkali metals, as you heard, they all fizz and react with water very violently. So that whole group were recognised as something that were very similar to each other. And so then people began to look for ways that these similar elements might be put together in an arrangement.
If one looks at the periodic table, so far over to the left, that's what we call group 1, and they're the elements, the alkali metals you've been mentioning, that fizz when we drop them in water. What's the difference between the ones right at the top left and as you go down that block on the far left-hand side, how do they change physically, the elements?
Well, they change in a number of ways. I mean, the most basic thing is actually that they get heavier as you go down the group. So the individual atoms are increasing in mass. In fact, lithium, sodium, and potassium are all light enough that they would float on water, but actually rubidium and cesium would sink in water, but then they would react very violently in it. But there's also more subtle properties as well. So, for instance, how easy it is to remove that outermost electron that all of those elements share becomes easier and easier as you go down the periodic table. That means, in a sense, that those metals become more reactive.
So the ones on the far left are all metals. As we move across to the right, you get into the group next to group 1, the alkali metals, and they're a bit less reactive, aren't they? Things like magnesium, but they behave in a sort of similar way. And then as you go across, what changes?
So as you're moving across the periodic table, what is happening is you're adding one extra proton in the heart of the nucleus. And so this, in a sense, will hold all of the electrons sort of more tightly in. And so then it's harder to remove the 2 electrons from the next group. And actually, by the time you've got all the way across to the right-hand side, it's very, very difficult to remove any of those electrons. And it's actually their properties are more that they would accept electrons. They would gain electrons and become negatively charged ions in some cases.
I remember my chemistry teacher putting a sort of ruler across the periodic table on the far right-hand side and saying everything to the left of this is a metal and the things to the right of this ruler are non-metals. And there are far more metallic things that behave as metals than there are non-metals. Why is that?
That's quite difficult, actually. It's all to do with the number of electrons that each atom has and how they can form bonds. And actually, you only get molecules within the elements for the right-hand side of the periodic table when, for instance, you get 2 oxygen atoms forming an oxygen molecule. But for the other ones, you get larger structures with fewer electrons trying to form weaker bonds between all those. And that's typically a metal, really, with sort of these more, well, we call them delocalized electrons that can move around more easily throughout the whole structure.
Now, when Mendeleev put his table together, it didn't look like the one we have today. He actually left gaps. Was that because he realised there was this periodic behaviour? Things did follow a pattern and a sequence of behaviour, and so he knew that even though we hadn't discovered something yet, there had to be something that would fit with that sort of position in the table. Is that where those gaps originated?
Well, of course, I mean, Mendeleev wasn't the first to draw up his periodic table, and others before him also left gaps for elements that were yet to be discovered. I mean, the real difference with Mendeleev in his periodic table is actually that he very accurately predicted the properties of those missing elements and their compounds, and when they became discovered, that's what really drew people's attention to his system.
When was the sort of golden era for discovering elements that loads and loads of them began to appear and fill in the table?
Well, to fill in the table, you had to have a table, but they do come in sort of spurts. But I mean, one of the key things actually in the late 1850s and early 1860s was the discovery of spectroscopy. So that revolutionized the discovery because remaining elements at that point were very rare in a sense, so hard to find. And so you needed a very, very sensitive technique. And that was the flame test idea that allowed some elements to be discovered all in one go.
I'm glad you brought that up because we're going to hear about the pioneer of that, Robert Bunsen, next. But sitting in front of you, you have something exciting that you wouldn't reveal to me earlier. What's that?
So this is actually a copy of the very first periodic table, which is 7 years before Mendeleev's version. You say that Mendeleev's version looks very different from the modern version. Well, this one looks completely different. This one was designed to be wrapped around a cylinder, and actually it has a continuum of the elements arranged by their weight, as Mendeleev also arranged them, of course. And on this version, the elements with similar properties also align vertically in groups.
Where did you get that?
So this one is owned by St Catherine's College and will be on display there in March and April this year. We will be showing this very first form of the periodic table and indeed a number of other versions, including Mendeleev's first versions as well.
So go and have a look and you can see what those tables look like. Peter, thank you very much. That's Peter Wuthers, he's from the University of Cambridge. And someone actually wrote this joke for me. I get done for my jokes terribly, so I'm going to read it, but I do not take responsibility. It says, I was going to make a chemistry pun at the end of that interview, but all the good ones are gone.
Oh dear.
I didn't get the reaction I was
Well,
looking
I mean,
for.
I thought it was hilarious personally, but there we go. Now, 150 years ago, the average scientist lab looked rather different to the ones we have today. For one thing, the light bulb wasn't around. So how exactly did scientists test what each element was beyond just looking at them? I went to Anglia Ruskin University to find out with the help of forensic scientist Lisa Ferguson.
Well, they typically use flame tests. So what they would do is put individual elements into a flame and the flames would give characteristic colours, and that's how they identify different elements.
Remember those Bunsen burners from school science class? You've got a gas inlet and a valve to control the airflow, and these burn together to produce a clean flame, crucial for doing a flame test. And this was something that chemist Robert Bunsen, back in the 1850s or so, was particularly interested in.
He originally started work on flame tests, but he found that the flames that he was using sometimes produced soot and weren't necessarily clean flames and sometimes interfered with the actual colours of the elements he was trying to get. And so what he developed was the Bunsen burner, because that gave you a flame that was non-luminescent and therefore did not interfere with the colours that the actual elements produced when they were put in the flames.
So what's actually going on in a flame test? How does burning an element tell you what it is?
As the actual element is heated up, the electrons in the element get excited and they go from what we term a ground state to a higher energy state. So when they're in the higher energy state, they then drop back down to the ground state, and as they do that, they emit wavelengths of light, coloured light, that is characteristic of the element.
Almost like jumping up and down.
It is indeed. It's a little bit like jumping up and down a ladder. On a ladder, you can step on one rung to the next rung, but you can't step in between the rungs. So that's a little bit like the energy levels.
And the distance between the rungs is separate for each element.
It is indeed. And so when they actually emit light and it drops back down to the ground state, that would be characteristic of the element.
Well, that's the theory down. Now let's put it into practice. Once me and Lisa were kitted up with lab coats, safety specs and gloves, we got stuck in. We've got a Bunsen burner, some matches, just putting the gas on now. Let's get this Bunsen burner lit. Now, what are you holding and what are you about to do?
It's just an implement that's going to enable us to actually put the element that we're looking at, in this case copper, into the flame.
But you're going to clean it to make sure we don't get any contamination?
Yes, I'm initially going to clean it with hydrochloric acid and then put the implement into the flame. So it just makes sure that any contaminants that may be present are no longer there.
So you're not doing a flame test for the wrong thing?
Absolutely, yeah.
So you've got some copper pieces. I guess the idea is to attach it to this implement and then see what happens when you put it in the flame. Oh, Oh, that does look a bit greener or a different kind of blue.
Yes, you can see the characteristic sort of green flame that you do actually get with copper.
Is this how fireworks work? Because you get lots of different colours in fireworks and there's lots of different metals involved.
Yes, so fireworks typically contain lots of different metals. When they're heated up, they actually emit energy of different wavelengths, which is the different colours that you actually see.
Ah, okay, a flame test in action.
Mm-hmm.
Very expensive flame test. So what colours would you typically see with other elements?
So with sodium, you typically get quite an intense yellow colour. With potassium, a lilac colour. With lithium, it tends to be a red colour. So there's some of your basic elements. Bunsen and Kirchhoff, by using flame tests coupled with a spectroscope, actually identified 2 new elements, cesium and rubidium.
The spectroscope that Lisa mentioned contained a prism inside. Think Pink Floyd's Dark Side of the Moon album cover, which splits light into all its coloured components. They found that the lines that appeared within the spectrum corresponded to the light being emitted by the elements. The wavelengths of light that each element emitted was unique, and this is why a spectrum is often thought of as an element's fingerprint. So are scientists using these same techniques to identify elements now?
We don't typically use flame tests. We've got sort of more advanced techniques that we tend to use to try and identify elements present in samples. Typical technique that we would use is something called inductively coupled plasma optical emission spectroscopy, or ICP-OES.
I can see why it has an acronym. Carry on.
And so basically it works on the same sort of premise, really. You've got, let's say, a sample of pure element. The actual instrument would suck up the sample into something called a plasma. It has a really high temperature. So when the sample is in the plasma, the actual solvent it's in evaporates off, and the actual elements there are atomized. And what happens is that the electrons in the elements again get excited from a ground state up to a higher energy state, and it's different for each element. And as they fall back down to the ground state, the elements, they emit a light of a specific wavelength.
As it turns out, it's not just flames or even plasma that can be used to excite electrons in spectroscopy. Other wavelengths or parts of the electromagnetic spectrum can get involved.
So different parts of the electromagnetic spectrum have different energies associated with them. So something like X-rays is very energetic. So it's so energetic that actually when you irradiate a sample with X-rays in a technique like X-ray fluorescence, what that causes is actually electrons from the core, the inner electrons, one of those to be ejected actually out of the sample you're looking at. So because this electron is ejected from the core, one of the outer electrons drops down and fills that unoccupied space. And because the electron has gone from a higher energy outer orbital to a lower energy inner orbital, it gives off a X-ray that's characteristic of the actual element you're looking at.
Exciting stuff. Lisa Ferguson there from Anglia Ruskin University. On the way, why are some people so good at accents and the mysterious materials waiting to be discovered? Stay tuned.
Now, from identifying elements to safeguarding their futures, how much of each of these elements actually exists on Earth? And are we destined to run out? Well, with us is Lizzie Ratcliffe. She's from the Royal Society of Chemistry and is hopefully going to tell us. Welcome to the programme, Lizzie. Peter mentioned how we have a periodic table with all these elements listed, and that tells us something about how the elements behave. But what it doesn't tell us is anything about how much of each of those there is on Earth, does it?
No, it doesn't. And it's something we need to start thinking about because we're very aware of sustainability as a thing, things like plastics or energy or fish stocks or sustainable housing. But what we don't think about is certain areas of the periodic table that we might not have heard of. So I don't know if you think about whether yttrium is sustainable, but actually it's not. All the naturally occurring elements, you have to dig them out of the ground. They're in mines. And once they're gone, they're gone. And a lot of them we're using in our daily lives, and we don't even know it. So many of the rare and precious metals are present in our electronic devices. So in our mobile phones, Xboxes, smart TVs, pretty much everything we use. So everything we need for modern tech comes from this part of the periodic table where there's not a lot there. And we need to be careful,
the elements are not all made equally in terms of abundance. And some of them we really like, but there's not much of them on Earth.
Yeah, exactly. So there's plenty of aluminium, there's plenty of iron. We're not going to run out of pots and pans anytime soon.
That's good.
But indium, some people think it might run out in the next 50 years. Some people think it might run out sooner.
When you say run out, does that mean literally, because I've got an old mobile phone sitting in front of me here, I understand there's something like 30 key elements go into just making one of these. But when you say run out, does that mean that basically we've made so many mobile phones that all of these rare elements are in all these devices and in active service, so we haven't got enough of the element left to dig up?
The thing is that most of us aren't really recycling our mobile phones, and they're not made in such a way that they're easy to recycle. So the concern is that they could all end up in landfill. So at the moment we're digging out of the ground, we're using them, but we're not putting them back into the system. So there really needs to be a circular economy where we can plough the elements back in. Otherwise, yes, they will run out. If they end up in landfill, we won't have them, and not just for technology, but for other things as well. So a lot of the elements we're using in our phones, they're also used for aircraft engines, drill bits, hearing aids, pacemakers. They all have all these uses, and we don't even know what some of them might be needed for in the future while we're squandering them on our mobile phones.
This old phone, it's very old. It's a clamshell type of phone. That says how old this is. But there will be a suite of materials in there which will have been used to manufacture it. Are they easy to scavenge back, though? So if I took it upon myself to recycle this, how easy is it to get things like indium out of that so that you could reuse it?
It's not particularly easy at the moment, and part of that is because manufacturers are making them in such a way that they're not easy to dismantle. So some manufacturers make them with custom screws or special glues, so you can't just break them apart. So that's a big problem, and even when you do break them apart, getting the elements out isn't that easy. But if we start thinking about that at the manufacturing stage, it could get a lot easier.
But I'm surprised, given that we've learned our lesson in so many ways, so many times in the past about things like this, with squandering resources and using them sensibly and making them recyclable. Plastics, we talked about earlier in the programme, classic example. Why are we not doing this with these elements in these?
Well, this being the International Year of the Periodic Table is a great time to start thinking about that. It's just not made its way to the public consciousness yet. I wasn't aware until I started doing this research as part of our celebrations. I wasn't aware of how many rare elements are in my phone or in any of my devices. It's just not something that we think about a lot yet.
But if I take it upon myself to have responsibility and recycle my milk bottles or my wine bottles, not many of those, of course, I'm a very responsible drinker, but I know exactly what to do with them. So what can your average person do with an old phone like that to make sure that they are safeguarding our element future?
The Recycle Now website has a facility where you can put in your postcode and it will tell you what recycling facilities are nearby.
But are there any? That's the key
actually,
thing.
What we found is there's not. I've tried, and there's not consistency across different councils.
Because the Royal Society of Chemistry, a pretty potent organisation, they can lobby very hard. Is this something that you're going to start pushing this year and say, look, we need to be more responsible about this? We might have, it sounds like a long way away, 50 years, but that's time's passing quickly and we're going to run out of these things pretty fast.
We're doing a piece of research right now to demonstrate the scale of the problem and find out how many people are hoarding devices, and we'll be able to start producing some advice for government, manufacturers, retailers and individuals on how we can protect these precious elements better in future.
Lizzie, thank you very much for joining us. That's Lizzie Ratcliffe. She is from the Royal Society of Chemistry.
Now, we've covered the past and the present of elements, but what about the future? In another 150 years, could the periodic table look any different? With us is Kit Chapman, author and comment editor for Chemistry World magazine. So, Kit, we've discovered 118 elements so far. Is there space in the table for more?
There's lots of space. Don't worry about that at all. At the moment, two groups are even working to try and get the next two elements. And they're actually in a race at the moment in Russia and Japan. So we're expecting that there's going to be another two elements, hopefully within the next 5 years.
Now, are these man-made elements?
Almost certainly. So they don't necessarily have to be. There are theories that saying that you could find those elements on Earth, some of them, but at the moment, all the elements we're discovering past uranium, which is element 92, have been first discovered by a man-made project. And so these elements are probably going to be found in particle accelerators, and we're going to be making them a single atom at a time.
So if you're hinting that there may be some naturally occurring ones we just haven't found yet, where might they be? Haven't we looked in lots of places?
That's a very good question, and we have looked everywhere. In the 1970s, we looked in the BART system, that's a tube system in San Francisco. We looked in salt mines, we even looked in churches, because there was a theory that you could find it in the lead lining of stained glass windows, and you could find traces of those super heavy elements, as we call them. But so far, we've not found anything. There was a group from Israel that claimed they found element 126. Again, that's never been proven, but in theory, they could be some of those elements, and this is because of something called magic numbers. So we talk about electrons having shells, for atoms. There's a good theory put forward by someone called Maria Goeppert-Mayer that neutrons and protons also have these magic numbers of shells, and that balances everything out and makes them much more stable. Now, these elements that we're finding at the moment, the ones we're making, they last very, very small amounts of time. So element 118, for example, lasts less than a thousandth of a second. It's 7/10,000th of a second.
Wow, okay. I'm just trying to wrap my head around that. So, talking about making new elements, can we just cycle back to how you actually do that?
Yeah, sure. So there are two ways you can do it. The first ones, past uranium, were made through essentially what we now use as nuclear reactors. So it's something called neutron capture, and the idea is that you bombard something with neutrons, and through radiation, something called beta radiation, a neutron turns into a proton and you move one place up the periodic table. These days, we've got a particle accelerator. So you get a giant magnet and you make ions. That's a nucleus of an element like calcium, for example. That's element 20. And you make it go faster and faster and faster, and you fire it as fast as you can at a target. And if you collide with the nucleus, usually it explodes in something called fission. That's not what we want. What we want is fusion, where the nucleus sort of gloops together and forms a larger atom.
Is there an upper limit to how many we can make?
Well, we don't know. We think the upper limit is about element 172 or 173 before everything will just become too unstable. So that means we haven't found around a third of the elements that could exist.
Wow, so there's a lot to keep chemists busy.
There's a lot to keep chemists busy and physicists, because it gets really weird as well. Because we're making these things bigger and bigger and bigger, we start getting something called relativistic effects. And that's like Einstein in the theory of relativity. It starts affecting how the electrons behave, and things get very, very weird. We could have nucleuses that twist into the shape of a donut, so there's a hole in the middle. We could see electrons orbiting through the nucleus, and so all of this means that the periodic table gets very, very weird indeed.
So how weird do you reckon it's going to get? How far are we going to stray?
It's possible that there might be an area where chemistry just simply does not work. The elements become so strange that they would exist as cations only, as we would call it, so it wouldn't be able to attract electrons. Very, very strange. At the moment, with element 118, we're already seeing that weirdness. So earlier we were speaking about how elements in groups have different properties as they go down. Element 118, oganesson, is in theory a noble gas. It should be a gas at room temperature. It shouldn't react very much with elements at all. Oganesson, however, we think is very reactive and is actually a solid at room temperature. So it just stops following the rules completely.
So potentially new discoveries may well break the periodic table.
We might already have broken the periodic table.
Wow, okay. Well, we're going to have to leave it there. Thank you very much. That was Kit Chapman. And look out for his book, Super Heavy, Making and Breaking the Periodic Table, which is out soon. Thanks also to our other guests this week, Peter Wuthers, Lisa Ferguson and Lizzie Ratcliffe.
We've just got time to sneak in our question of the week. Adam Murphy has been tackling this question from Leah.
So why are some people good at imitating accents and doing impressions while others simply aren't? Obviously you can get better with practice, but why are some people born with the skill of imitation and some aren't?
Do you call the letter after Q R or OR? Is it Bath or Bath? There are nearly as many accents as there are people who speak. But why does that happen? Jonathan Goodman from the Cambridge Language Science Department filled us in.
I think there are two layers of answers to this question. The obvious explanation has to do with upbringing, although there's likely an element of natural talent involved. Just like with stage acting, we know, for example, that if you grow up bilingual, you'll be more effective at speaking in the appropriate accent in either language, and probably in foreign languages generally. So there's probably an element of exposure to multiple languages, and by consequence accents, within a particular window, usually about the first 10 or so years of life.
So, if you grow up around loads of accents, you might be able to imitate them easier. Maybe all our exposure to American television on this side of the Atlantic might give us an edge. But there's more to it than that.
The second layer, I think, has to do with the evolutionary origins of human communication. Some research in linguistics and evolutionary anthropology suggests that the diversity of languages can, at least in part, be explained by kin, or according to some group selection, whereby the pronunciation of particular words signals a connection with a certain kin or group.
Like a sports jersey for our vocal cords, then.
The classic example is the biblical case of Shibboleth, in which, after a battle between two tribes, the victors distinguished between their own tribe and the enemy by asking everyone crossing the river to pronounce the word Shibboleth. Members of the defeated tribe were known to pronounce the word differently, allowing easy distinction between those in the group and those not.
That might be an extreme example, but it shows the importance of accents for being part of a group.
If accents evolved, at least in part, to allow people to distinguish kin from everyone else, we'd expect this to have profound implications for how language evolved and continues to evolve. We might then expect people with more diverse linguistic or even genetic backgrounds to be able to emulate foreign accents more effectively. But until more extensive research is done, we can't say for sure.
Thank you, Jonathan, for lending your voice to that. Next week, we're hitting the bar for an answer to this question from Donald.
How does ethanol interact with the brain, and why does it disproportionately affect the area involved in behaviour and movement rather than the parts of the brain involved in vision, hearing, touch, or the brainstem involved in breathing, blood pressure and heart rate?
And if you think you know the answer, you can email chris@thenakedscientist.com. You can find us on Facebook, tweet @NakedScientists, or you can join in the debate on our forum, thenakedscientist.com/forum.
And there we must leave it. Thank you very much to Jenny Gracie, who put the programme together. Next week, we'll be looking at the Cambridge Half Marathon. Georgia Mills has been strapping on her trainers for a show all about running. The Naked Scientist comes to you from Cambridge University. It's supported by the EPSRC and Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.